Hey everybody, my name is Paul, W1VLF. Welcome back to the lab. Haven't made a video in quite some time, and I thought this one might be of interest to a lot of different people because I've been getting questions on some of the short videos that I've done about my optical communications experiments. And I don't know, maybe some of you know that I've been really interested in point-to-point or reflective path optical communications, and I did a presentation for the New England Weak Signal group on how to build, what to expect from your optical communication system, how to build receivers, how to build transmitters. This is a big array of diodes, and I think what I'll just do is go over on the computer and go through the PowerPoint presentation and see what happens. It's been a while. Like I said, it's been a while. I'll tell you what, we're dealing with infrared, okay? Inferior to red, so you can't see it, infrared. So I'll turn on this transmitter, and you'll see in the back, probably even hear it. Let me pull the tape off real quick. So this is just sending CW, and I'll try to point it towards the camera, and even with extremely high intensity, you probably barely see the LEDs turning on and off. You cannot see them at all in real life. So anyhow, let me run over to the computer and do a voiceover over the presentation and see what you like. If you're interested, hang around. If not, well, pick and choose wherever you want to be on the presentation. Thanks a lot. W1VLF. Okay, so W1VLF here behind the microphone at the computer desk, and let's get right into it. Basic light communications, just something that I had a lot of interest in over the years, and here's some of the topics that we're going to cover. What my basic strategy, what does that mean? Well, as anybody who ventures into some sort of esoteric area of experimentation, you find out that, especially when in the 1990s when I was doing this, you find out that there's not a lot of people to play with, right? Maybe there's a guy out in California or something, and the internet has brought us a lot closer to be able to share all our experiences. So my basic strategy was always, since I don't have anyone to play with, I'll use reflective paths, whether it was off of a building or off of clouds, things like that, where I would put the transmitter in one location and move to the second location with the receiver to receive the signal and make notes and do some experimentation. I'd like to thank Fred K1 FMS. He got interested, and now I have somebody to play with, and actually a bunch of other people too. So I thought this would be of general interest. The next thing is eye safety. Now, like the 10 gigahertz guys and microwave guys or anyone, you wouldn't stick your eyeball down a waveguide with 10 watts of RF in it. Just like you wouldn't sit and stare at the large array I showed you before. It's a 6-degree beam width, so the light spreads pretty quickly. But we're going to talk about that in the next scene here. But just use common sense, right? Don't stand in front of the thing for half an hour looking into it, trying to say, hey, can I see it? Can I see it? No. It's not good. So at your own risk. Beam angles, we'll talk about beam angles. People are always asking, why don't I use lasers? It would be so much easier. Well, there's reasons why I don't use lasers, and when we cover beam angles, we'll talk about that. My first cloud bounce experiment was in 1998. It was 3.5 miles over ground, if you want to call it, say like that, but over 5 miles when you consider the sky path. And I also have audio of that and the path, so you'll see that later on. And bandpass filtering. Bandpass filtering applies here just like it does in the RF world, only it's an optical bandpass filter. We're using 940 nanometers. Why 940 nanometers? Because back in the 90s, I worked for a cable company, and I could get all the old remotes for free, and you'll see more about that later. And they were on 940 nanometers, so I kind of stuck with that over the years, as I developed new receivers and transmitters and whatnot. Your biggest foe, the biggest fight is going to be noise, and so if you're expecting to do this in bright daylight, you can manage 3 or 4 miles, but I don't think you're going to see big DX records. And we'll go into some of that as well, because I have some nice slides that show a weak signal source at a given distance, and over ambient light changes from day till night, the weak signal source doesn't change in the amplitude, but the signal to noise ratio tremendously changes. We'll talk about detector size. Oh, go away. It's a spam risk. Should I have taken it? Detector size is important for a bunch of reasons. Capture area and being able to actually aim, because some of these receivers, depending on the size of the lens, the focal length of the lens, and also the detector size, you have a beam width of roughly a degree or two. And that makes pointing, until you get used to it, sort of like pointing a 10 gig dish, only probably 4 times worse. But you get used to it at some point. You get a feel for being able to point this thing. We'll talk about simple transmitters and receivers. Antennas, lenses are antennas, transmitters are LEDs, and what you do with the light power that comes out of the LED. And we'll also talk about real world experiences, starting back in '98 when I did that first cloud bounce, to cloud bounce in more recent terms, which you may have seen on the other videos that I did. And also point-to-point communications between Fred and I. So that's one of the things that all this stuff will go into detail. So again, my basic strategy started in the 1990s. Free LEDs. Free in the sense that I didn't pay for them. Not free in the sense that I had to remove over 800 of them from remote controls, test each one, and build an array. That took a lot of time, but in the purest, they were free. I was coming home with boxes and boxes of large boxes full of remote controls from the cable company that were being thrown out, and pull those diodes out, check them, go and then build the array. So like I said, there's no one to play with. Okay, we're down over here. There's nobody to play with, so you've got to try reflected paths, cloud bounce, so you have someone to play with. Essentially, I was going to say essentially you're playing with yourself, but that's probably not a good way to put it. You are the transmitter and the receiver path. A friend of mine, Nick, W1ATT, allowed me to put the transmitter at his house back in the 90s, and the receiver was at my house at the W1 VLF QTH. The terrestrial path was about 3.7 miles, and the sky path was 5 miles. And the evening we performed that experiment, the ceiling height was 10,000 feet. And if you did the math, you came up with, I forget what the angle was that he needed to point at and I needed to point at, so that we would have it intersecting beams. The receiver beam width and the transmitter beam width would like illuminate, sort of like troposcatter, right? You have a common volume that you're illuminating. And then, the question that comes up a lot, why aren't you using lasers? And we'll talk a little bit about that. So, eye safety, I think we covered that. We can't see 940 nanometers. The math gets very involved to calculate safe exposure distances, so don't look into them. Handle with care. The array that you'll see, not the 1998 array, but the newer array, the one I showed in the opening, has 140 diodes running 100 milliwatts each at 50% duty cycle. And so safe distance is unknown, but it's not like a laser. Some more stuff here. Practice safe lens at all times. Stay away from the front of the thing. You'll probably be better off for it. To give you an idea, typical laser, okay, and you think pointing a 1 degree receiver is bad. A typical little laser module you can buy out of China or wherever for $5, $10 has about a 1 milliradian dispersion. That they don't call it beam width, they call it dispersion. And that dispersion, when you find out what 1 milliradian it is about 0.057 degrees. That's a real son of a gun to point. Okay. It can be done, absolutely, but it's very, very difficult. These Vishay diodes are 6 degrees wide, so that's a little bit easier than your 2-foot 10 gigahertz dish. So that works out okay. So let's take a look at what does this 1 milliradian mean. All right. So over here we have a laser with a beam width dispersion of 0.057 degrees, and here we have the LEDs, the typical Vishay 5490 LEDs. That's wrong. That should be 5940. So that, if you're looking up that number, that is incorrect. It should be 5940, like the wavelength of light we're using. So you point a laser and you go out, what's the distance here? 1,000 feet. 1 milliradian equals roughly a 1-foot diameter. So whatever power you have from this laser, call it 5 milliwatts or 10 milliwatts or 100 or a watt, whatever it is, it has only spread to the diameter of 1 foot at 1,000 feet. That's still potentially, depending on the laser power over here, and the fact that we're dealing with light waves that don't make us blink because we can't see them, so there's no blink response. Those are, that's still, in my opinion, dangerous. Whereas the 6 degree beam width of the LED array is now, that amount of power is scattered into a 100-foot diameter. So the power density is relatively low here at 100 feet. So that's one reason why I don't use lasers, is they're dangerous up close. We don't blink on 940 nanometers. And also, you buy a laser, on eBay, it typically comes from China. It says 5 milliwatts eye safe, but you really have no idea of what kind of power is coming out of there. Just not worth it. I have a couple of cameras that see infrared with spots burned into them, into the CCD device, and that was because the laser passed by it. So I have not worked with lasers for this kind of communication system in quite a while. So people are going to say, well, that's a lot of infrared energy, from those 140 diodes. And so Fred came up with this idea, and I built one of these. And okay, so if you look on the right side first, up here, 6 feet from my high power array of 940, that probably should, I have several 940 arrays, that should probably be 6 degrees. But 6 feet away from that high powered array, we have a half scale in microamps, right? 50 microamps. The detector is up here. Can't see it in this picture. Okay. On an overcast day, when you stand outside, that meter is pinned, so I have no idea how much more it is. So at 6 feet away from this high power array, you're already at half of what you're exposed to at 940 nanometers outside. And by the way, this is the detector up here. So essentially it's just a little solar panel with a bandpass filter in front of it, one that restricts most of the visible light and only allows the infrared light to pass through. So what happened? Okay. So you're saying, well, I have 140 of these LEDs. How far before they actually combine into a single beam? And you take 6 degrees. Let's see. Let's see. I forgot how far. I guess I forgot to put the distance in between these two. So, but anyway, you can look at, here's one LED and here's another LED. And at some point, those two cones are going to overlap, right? So if you take those same two LEDs and you say, oh, they're 1 inch apart, those two cones are going to coincide at 8 inches. The reality is those LEDs are 0.375 inches away, and they're already half, 50% coaxial, if you want to say that, at 8 inches. So once you move out further and further, they form one beam. You know, it's sort of like looking at I don't know, headlights or some multi-source illuminator from a great distance. It appears to be one source until you get close enough to actually distinguish, hey, that's, you know, like for instance the LED lights, traffic lights. When you're a couple hundred feet away, you look at that and you go, that's just a green dot. But then when you're right underneath it, you can actually see each LED. So that's what happens here is you're combining power. There's no phase, right? So you don't have to worry about this LED and this LED and spacing and wavelengths and phasing lines coming up to them. There is no phase, there is no polarization, there's nothing like that to worry about. This stuff is ultra simple when it comes to that. Let's see, did we cover most of this? Yeah, we did. Here I'm talking about why not lasers and whatnot. So I won't go through that again. But basically, I'm not you do whatever you want. Practice safe light, safe lens. But we made it. I guess I could say now we made easily. Fred and I made 25 miles with the LED arrays that we're running. You'll see a lot more about that later on. So I'm not even going to do the anything to do with the lasers. We'll just pass on that. So cloud bounce in 1998. So you think about that. That was 95 would be 30 years ago. So I don't know, 28 years ago, something like that. Here's the LED array that I built. Each one of these LEDs that you see in this array, I think there's 7. 1, 2, 3, 4, 5, 6, 7. I think there's 7 in here, and each one of them has its own. Each string has its own balancing resistor, and then all those series strings are in parallel. You'll see a picture or a schematic diagram later on. But the beam widths here, think about this for a second. The beam widths here are 60 degrees, plus or minus 30 degrees. So when you hold a remote, your main objective is to change the channel on the TV. You don't want to be looking through a rifle scope to be able to beam the energy right into that detector in your cable box. So they run these LEDs very broad, so that if you're off by 40 degrees or 30 degrees, it still really works. So these were free, but they weren't a very good way to get power density. Here's a close-up. So what is it? 1, 2, 3, 4, 5, 6. Okay, 6. There's 6 LEDs in series, and then on each one of these legs here is a maybe 10 ohm resistor. I don't have this array anymore. It's long gone. But again, removing these 800 and something LEDs. I think my wife thought I was nuts. Well, I was nuts. I'll have to agree with her on that. But that's just a closer look, okay? So let's say this side of the array goes to ground, and this side of the array goes to a 10 ohm resistor in series with the switching voltage that's setting the tone that's on these, okay? And they were in a box, and they were air pressurized. I forget how many amps this drew at 12 volts, but it was considerable. But the power density was very, very low by today's standards. And you could see this. I took these pictures with something called a Snappy, if anybody remembers those. These were, I think, analog pictures or something. I don't know. Very low resolution, though, because you should be able to read all that stuff on the back of the fans and whatnot. So here's the path. What did that path look like, right? What did that path look like? So this was my QTH. Again, these are from ground level. And so Nick was over here. He was looking up at, I don't know what, but the common volume was up here somewhere, right? There's no way that there's a line of sight path between the two of us. So if you took this line and sort of stretched it up here somewhere, that's where the common volume was. And as soon as you pointed away from that, it would go away, your signal would go away, and as soon as he would move the transmitter, and then I'd search around the sky and I'd find him again and go, "Hey Nick, did you point it this way?" And he goes, "Yeah, how'd you know that?" I said, "Well, so anyway," and here's some of the recovered audio. This recovered audio really doesn't sound that great because I had to use such a narrow bandwidth. There was a program called Cool Edit that I used to filter this. I'm going to pause that for just a second. That is just a carrier before my call sign. So, and if you listen to the carrier, you'll see that there's QSB on it. There's actually from testing, there's actually all sorts of QSB, but there's like two major, one long-term QSB over the course of many seconds, and then other ones that are, almost intercharacter depending on what's going on in the path. So let me move this up a little bit because that's just the tone for the first 30 seconds. Play it. Okay, pause. Okay, so I guess everybody probably got that. This is an illustration of what the transmitter looked like from New Hartford to Harwinton. Not to scale, obviously, but just gives you an idea of what was happening, right? This beam was looking up at the sky. Picture a big spotlight, like during World War II or whenever there's a new car, dealership opening, they have those spotlights, and it illuminates part of the cloud. Actually, this is the transmitter illuminating the cloud, and as long as I'm pointing at it and I don't have a lot of ambient light, I was able to actually make the contact. Now, with the system I have now, I have, compared to this audio that I just played, I probably have conservatively 30 to 40 dB of headroom over the top of what you heard there. And this is the receiver. This was an 8-inch lens. I think I got this from Larry, WA1LGQ, good friend I've known forever and ever and ever, ham radio friend. He got this somewhere and we made some kind of trade, and the detector sits back here inside the aluminum tube. Very, very, very crude by today's standards, but it worked. And again, it was the 1990s. So when I say fighting with the sun, what do I mean by that? What I mean by that is the sun, like for instance, if you have a 10 gigahertz dish and you don't know if it's working properly, you there's some calculations you can do. You point at the sun and you see how much of a noise floor rise you have on 10 gigahertz. And that says, based on, I have 4 dB in sun noise. I have a 3-foot dish. I have this kind of feed. It's this time of year. I'm pointing this direction. You could sort of validate the system that you're using. But here is the response of a typical photodiode. And they vary slightly, right? Some have a little more enhancement here, some go up a little higher, but we're operating at 940 right here at the knee. So why am I showing you this? Because at 940 nanometers, that's your interest right here. That's what I want to see. That's what my lens, my optical system wants to see. All this other crap, and look at the amplitude here, is just noise. Absolute just noise, even up, and in fact, there's noise on 940 nanometers, which you can't get rid of unless the sun goes away, which happens at night. But this is all noise. So how do you get rid of this? Well, you go to an optical filter. So here's that 940 nanometers, and you can see that percentage-wise, it's down significantly at 900 and at 960. Whoop, backwards. Let me go back. So you're just taking a slice out of this. Just like you'd put a bandpass filter up ahead of your HF rig or whatever, you need to have an optical filter. At least during the day. At night, there's not enough, I don't think, IR to cause a real problem. But if you want to make any kind of daytime contacts, you are definitely going to need to do something like this. Stick this right up ahead of the optical detector, and it cleans up a lot of that stuff that's down here to 400. So here's a test. Why, okay, what kind of a big deal is fighting with the noise? Excuse me, the sun. Well, let's. I have a weak signal source. I'll show you it. I'll show it to you later. It's nothing special. All it is, and you can build it anyhow you want, any way you want. All you need is a single LED, and you need to turn that LED on and off at some rate, right? And the rate that I chose was to stay away from audio because I didn't want the detectors detecting, second, third, fourth, fifth, sixth, seventh, 10th harmonic from 100 of 60 hertz or 120 hertz or God knows what. So many things make noise. But so mine runs around, I think, 16 or 17 kilohertz. So if you disconnect the receiver, you get a noise floor on an SDR. This is amplitude going this way, right? And this is time. And the way I made this was I disconnected the optical receiver here and just took a reading for some period of time. And the noise floor showed a minus 125. So that was the noise floor of the bandwidth of the SDR I was using. So you turn on the optical receiver and guess what? It's going to make some noise. So it does. Okay, so there's 10 dB of noise there, right? And then when you're pointing away from the sun, not even having a weak signal source, you now have a minus 82, which is from this noise floor, 40 dB of noise plus, and you do the math. What is it? Let's call that 20 and 15. So 35 dB or so of noise that you'd have to contend with. So the guys on HF, if you're running a kilowatt, you're down to 1 watt, half a watt, something like that. So it's a real problem. And this is with the bandpass filter up ahead of it. So you can feel the sun on your skin. It's just an incredible source of noise. So I'll probably say this 2 or 3 times throughout this. Build a weak signal source. And I'll show you how to do that. Because you can't see IR light. So you don't know whether your receiver's working or not. You need a weak signal source. Just like on 10 gigs, 24 gigs, you have the Digi-LO for a weak signal source. You need something here, and you can do it all sorts of different ways. You can make it variable. You can make it change frequencies and for whatever your application is, but you do need something, right? You absolutely need a weak signal source. Otherwise, you're literally kind of blind because you can't see this stuff. Okay, so fighting with the sun again. I have a weak signal source. It's 150 feet away from my house. And here's 3 examples pointing north at the weak signal source. And my sons are texting me. I'm going to put this thing on quiet so I don't... Guys, don't you know I'm making a video? There we go. Okay, so the only thing that has changed is that we went from day to night. Okay, so if you look at this signal level here, the noise floor is minus 90 because of the sunlight. And this is, again, I'm pointed north, so I'm not looking at the sun. Oh, by the way, never point your optical receiver at the sun. You could say goodbye to your photo detector and probably half of the other components in there if the full sunlight falls on it. There's a funny story about that. I'll tell you a little bit later. But here's my weak signal source. Okay, look at the signal. Minus 80, minus 80, minus 75. So not a huge difference. But look at the noise floor. Minus 90 during the day. It's noon and it's overcast, so I got a little bit better signal to noise. It's minus 100, so now the signal noise ratio is 20 dB. And this is the dark sky at night pointing. The noise floor drops to 120, and so now you're at 25 plus 20 is a 40 dB signal to noise ratio. And this is what it looks like in the waterfall. The reason why you're seeing 2 carriers here is because this was a Q65 digital mode experimental weak signal source I was messing around with. But it's really, really dramatic. Okay, so you go from a signal to noise ratio of 10 to a signal to noise ratio of 45. Very, very dramatic. And so you need to, optimize your system to try to get rid of every piece of noise that you can, because you're fighting against the sun, which is the ultimate noise source, I guess. So optical detectors, there's no lack of optical detectors. I personally use this one. It's the PD49PI infrared optical detector. It's an optical detector. It's a little solar panel. It's a solar panel that's like this is encapsulated. The solar panel's in here. This is actually the back side of it. You wouldn't use that side. You'd use the other side, which is flat. But inside here, about 4 millimeters by 4 millimeters is the active area. The rest of this stuff is just for convenience and how to, because these were through-hole parts. I don't know how they were placed, but anyhow, you need an amplifier after this. So that's where this TIA or transimpedance amplifier comes in. This black surface here, this epoxy, this encapsulated epoxy, is a bandpass filter, but it's a very broad, not like a third, fourth order filter. It's very broad, but it does get rid of a lot of ambient light. But the difference between this and that narrow filter is night and day. This guy has no filter. You'd have to put a filter on this one. But the active area, if you look in here, is only 1 millimeter squared, right? And that has a big effect because it's receiving less noise because it has such a small area. But the problem with having an active area this small is aiming. Let's say your lens focuses the energy to an infinitely small dot. Well, when that happens and you're wobbling your receiver around, pointing it back and forth, you've got 5 millimeters square, roughly here, where that dot can fall anywhere on this surface. Damn it. Sorry. Let me go back one. That dot can fall anywhere on this surface here, okay? And it's still going to give you an output. In fact, you won't even know you're in the middle, on the left side, the upper left, the upper right, the lower right. You won't know where you are. All you'll know is you have a 1 degree beam width. Look at the size of this. It's literally 1.2 square millimeters. And now that same infinitely small dot can only walk around this tiny little... Why do I keep doing that? I keep hitting the mouse button. That tiny little dot, that infinitely small focused 940 nanometer light is falling only on this tiny little area here. And if it moves out 1 millimeter, well, you're out of luck, buddy, because it's sitting out here and it's not going to hit. So what are the consequences? Ooh, well, one consequence is you get a lot less noise than this one, okay? Because there's also remember that the dot that you're trying to focus onto this is infinitely small, or close to infinitely small. Picture it as like a ballpoint pen ball, and you're putting it somewhere here on the surface. And anywhere that you put that ballpoint pen ball, you're going to get signal out of it. But the only part that's doing you any good is that tiny little area that you've put that ballpoint pen. All the rest of this is picking up is just noise. Here, you have much less noise being picked up, and that ballpoint pen ball is still, 5 or 6 or 10 times bigger than the actual spot that you're aiming at. So all the rest of the noise that you're gathering over here is not seen here. So what's the problem? Well, the problem is you're trying to hold this with a big lens in front of it pointed right at, and it makes the beam width infinitely smaller than this does. Because you can afford to walk that small little dot all around here and not know, right? You don't know where you're pointed, except for you have a good receive signal. Here, you've got much less area to do that on, and you also have much less noise. But more optical detectors, right? These are called hybrids. Hybrid meaning that there's a diode and an amplifier in the same package. The problem with these, some of these are, depending on which one, you can look up the specifications and whatnot. The problem is that this detector is big enough, but these are like $1 a piece or something, and there's something called NEP, noise equivalent power. And what that means is, how much light power do I have to drop on top of this to equal the amount of light equal the amount of noise that's generated by this solar panel? And these are not really, they're pretty poor. They also have a very limited bandwidth. But they're very convenient to use, and they're extremely cheap. And if you want to use one of these and get started and play around with it, that's probably... I used one of these when I first started and then moved on. Here's a more expensive version with a much quieter amplifier and a much quieter piece of silicon in front of it. And if you really want, you use an avalanche photodiode. These things are probably 20 dB better in sensitivity. But it's an expensive little module unless you find them used on eBay. These things were like $50, but it was complete receiver, all built in. But the problem is don't even think about using these during the day. They're just, even with double bandpass filters in front of the detector, they're incredibly noisy. So anyway, that's just a little bit more about detectors. What do we got? Okay, so here's a really good example of why does size matter, right? In my weak signal source, don't know if you can see it or not, but you see where my mouse is? There's a tiny little white box there. Okay, that's the weak signal source, and the diode is infinitely smaller than that. So, what's this? Oh, this opening is about 10 by 10. It's less, but let's call it 10 by 10 just so that we can have, just for the topic, the conversation here, it's not critical. And if you look here is the image projected on a piece of paper. Okay, so look at that square image, and let me go back. That square image is the same size as this. Okay. And why does that matter? because all of this is noise. All of this is noise. The only thing I really want to receive is this, which is that tiny little dot in the very middle of the barn. That's my weak signal source. It's got a little antenna on it to lock it to my Wi-Fi in the house. Anyhow, but if you go back again and look, this is what's being projected onto my detector, and if my detector is this big, that dot is infinitely small, wandering around somewhere. That light dot, right? So that's why size matters. And in fact, if you put a blocking, make this light go through a pinhole, becomes incredibly hard to aim, but the signal to noise ratio goes through the roof. There's the what is it? The optical weak signal source. Oh yeah, build a weak signal source. You can't see IR light. So let's put together a basic system, right? The most basic system that you can. So you need a transmitter. Well, you can go on eBay, and for like $5, at least that's what they were back when I was experimenting with this, I don't know, a couple years ago when I first got these. Actually, I got these as little square wave generators with a 50%, with a variable duty cycle. So this moves the frequency up and down. They're adjustable from 1 hertz to 150 kilohertz. They're not crystal controlled, so if you want to use 20 kilohertz, it might be 18 or 19 or 20 or 21. But for this purpose, it's experimenting. It works out really great. So what comes out of here? A square wave comes out of here. Here's the square wave. And that square wave, to some extent, is a function of the voltage input. If you put 30 volts in, which they say you can, you're not going to get 30 volts out of here of PWM signal, and it's not going to blow up your diode. There's a current limiting resistor in there. But so power goes in. I ran them off 9 volts. The LED ran off of the 9 volts, but there wasn't 9 volts across the LED. But so now you have, what do you have? You have the baseline, you have 0 volts, then you have a plus voltage, and that for a period, then you have 0 volts, a plus voltage, 0 volts, a plus voltage, and this is happening at your choice of frequency. I happen to use, I think, 16, 17 kilohertz because I'm using an SDR for detection, and I don't like going down below 10 kilohertz. Fred and the guys like to use 600 hertz because they're listening by ear. That has advantages of a very simplistic receive system without the use of a computer. But if you go up to 16 or 18 or 20 or 30 kilohertz, then you can use an SDR with filtering, with all sorts of different detection modes and so on. So anyway, that could be a transmitter. Let's move on. Here's a transmitter right here. This thing, let's say we set it for 500 hertz, right? We go back, we set this signal for output for 500 hertz, 50% duty cycle, and you take that chain coming out, and you literally connect it right to a diode. Now you have a weak signal source. It may not be as weak as you want, but you have a weak signal source. And in fact, you have a transmitter. You insert a key where the arrow is, and you have a CW transmitter. When you key the transmitter, you connect this connection to here, and what happens is the LED, sends out a pulse, a dot or a dash of say 500 hertz, like we talked about before. So building something like this can be incredibly cheap and fulfilling. I mean, my weak signal source is many times weaker than this thing. And when you get to that point in your receivers, you need something like that to optimize focal points and all the rest of this stuff. But anyway, that's a basic transmitter. Stick a key in there on the PWM line, and you can be sending CW on light. So what's a receiver? Well, receiver is extremely simple as well. There's a photodiode. What's that? Well, it's a solar panel. Solar panel is making a square wave here because you're transmitting a square wave, right? It detects there's a small voltage here. Assuming there's no sun, what you would get out of this would be a square wave at 500 hertz from that previous transmitter into an amplifier, into a speaker. Ultimate in simplicity. Again, you don't get all the rest of the really, the IF bandwidths and all the stuff you can do with an SDR. That's a totally different topic. But it's simply a photodiode connected to an amplifier to a speaker, and lo and behold, you hear the modulated CW. So some of the choices for LEDs. I've spent way too much money on LEDs over the years. So let's talk about a little bit about some of these LEDs. This is a company is Vishay. Boy, and I got it wrong here too. That's supposed to be 940. Oh, crap. But these have a 60-degree beam width. This is a model of it, but it's pretty damn close to a 60 beam width. And what do I mean by that? By the 50% power line, it's plus or minus 3 degrees. So all that power is condensed into 6 degrees instead of plus and minus 30 degrees. You can do the math on that and find out how much more intense that is. It's very intense. Here was another failed experiment. This is a 100-watt LED, but in a 60-degree beam width. The amount of light energy falling on the detector was less than 2 of these things running in parallel, purely because it's not 100 watts. You never get a 100-watt LED when you order an LED from eBay. It's always a third of that. And would I build another array of... Okay, these are about 40 cents a piece, right? So 10 of them, $4. It's not bad, but there's a lot of building involved. Excuse me. Nowadays, you can buy LED spotlights with a 90-degree beam width down to 10-degree beam width. And these are, I think, 3 or 5 watt LEDs. So you take 5 watts times 1, 2, 3, 4, 5, 6. That's 30 watts of LED power, and squeeze it down into 10 degrees, and you've got an incredibly powerful transmitter without doing hardly any work. You do have to take it apart and put your FET in there and whatnot, but this is the way I'm going now. I have 4 of these things running. Oh Christ, I can't remember how much power, but because it's during the summer, I don't spend a lot of time on this. But so anyway, this is the way I would go. Fred tried one of these, and he calls it, what does he call it? The flamethrower turbo mode. I can't remember. Anyhow, this is the way to go. These were until the whole tariff thing started, these were like $20 for quite a bit of power in a 10-degree beam width. So, and all the real work was done for you. So, what if you want to do something more than CW? What if you want to do Q65? What if you want to test the limits of your of what you can say? Say you have a path and you can see the signal there, but you can't copy the CW. Well, here's what's going on here. And I have to give Renee a big thanks, because he's the one who did all the programming for the microcontrollers and the GPS and timing modules. But as you know, for Q65, you have to be right on frequency and right on frequency and right on time. So you need a GPS module. This assembly was like $10. These microcontrollers were like $4, and the IRL 540 logic level FET was another $3 or $4. This is the array you saw in the beginning of the video, and it's I wish I had those numbers down somewhere. I'm notoriously bad at documenting things. But it switches the high current for this FET array. But it's amps. It's, let's see, what do I have? 1, 2, 3, 4, 5, 6, 7. 7 LEDs times 10 is 70 in the top and 70 in the bottom. It's many amps. It's in the order of maybe 8 to 10 amps, something like that. So you can get an idea of what kind of power levels we're talking about. But this, I'll show you more. I'll show you more about this. So here's the more advanced receiver, right? Instead of just the LED, the photodiode here, you have a filter. Well, that gets rid of a lot of that visual light that we're not interested in at all. And you put a bigger antenna on it. What do you mean antenna? Oh, you put a lens that gathers the light from this huge area here and concentrates it to this part. Then you have an amplifier, and then you run an SDR. Now you can do Q65, you can do FDA, you can do CW, you can do single sideband. I haven't done that yet, but you can do all sorts of things once you get a more complex receiver system like this. This is purely because my choice. This is how I like to do it because I got more handles, IF bandwidth, demodulation modes, waterfalls, all that sort of stuff where I can analyze what the system is doing. I can't say this was an actual QSO, but this was a 4-mile. Well, I guess you could call it a QSO, right? Here's a 4-mile QSO. I had 2 transmitters. One was a single LED. You'll see it over here, right? Running at around 16 or 18 kilohertz, something like that. And here is the 144 array. This was a 4-mile contact. I put the stuff on one hill and went to the other hill and just let it run on the other hill. So let me play this audio and take a listen. Okay, if it wasn't apparent, that's the 140 LED array. That is just pure CW, very basic setup. I'm going to pause this for a second because that audio, my audio is very, very low. But this is the 140 LED array right here. And this is the one single LED. One of those 5940 LEDs, 45 cents. And the reason I did this was because at 4 miles, it wasn't nighttime, but it was 4 miles away. It was 4 or 5 o'clock in the afternoon, so the sun was nowhere near at its peak, and I wasn't sure I was going to be able to hear one LED at 4 miles. So I put the big transmitter up there and the little single LED transmitter up there, and I let them both run, and lo and behold, had good signal copy from both of those. So I'll continue on. Just forget about the fact that my other voice is in there at a very low level. And we'll switch over here to Q65. And you could see this is Q65, right? Because you could see the tones here. Let me turn it on and let you'll hear it. That's the carrier. Both of these transmitters were sitting side by side, and to be honest with you, I wasn't sure if I would be able to hear the single LED transmitter, this guy right here. So that's why I put the big transmitter up there. And this one's on 14.4 kilohertz, and this one is on 17.325. And I just wanted to make sure. I knew I could hear this one. I wasn't sure what I would hear here. Now, if you look at it in the previous photos or screenshots that I showed, you'll see that there is plenty of headroom. And this isn't even at night. This is, I don't know, 4 in the afternoon, 5 in the afternoon here with the daylight. I'm going to blast right through this. The noise, and I'll shut up. That's the Q65 signal. Pause it. So the single LED here at the best was 20 dB of the noise. The other LED was about 50 dB above the noise, right? So now you got to take these with a grain of salt. We're not using a calibrated spectrum analyzer. You know, who knows if I had them exactly pointed, but there was a 30 dB difference. When you can make a 30 dB difference, it's huge, right? Absolutely huge. Now, the other thing is, this 4 miles, right? 4 miles with one LED. This is Q65. Look at this next page. You can't see this really well, but I was getting a -4 was the first time, -1, then a 0, -1, then 0, then 1, then 1, and it kept on getting better and better as the night, you know, as we got closer to darkness, because the interfering sun wasn't a problem any longer. Yeah. So I had a lot of headroom. Q65 will easily see things down to -23, 24, 25. And here we are 20 dB above that. So that says a lot for a 4-mile path with a single LED. Some of the earlier QSOs, a couple of different transmitters here. This is K1FMS's transmitter. With 24 LEDs and also a bright green collimated LED for you're on a dark mountainside, you have no idea what you're looking at, and Fred had that LED on there, which was helpful in alignment. That's my transmitter, the 140, or excuse me, 140 LEDs. That's one of my receivers with the photodiode, and then the one on the end here is the avalanche photodiode amplifier combo hybrid, and the same lenses are in front. This one has a lens cover on it, or a lens shield. That receiver running the APD is at least 20 dB better when it's quiet or at night. So couple of QSOs we did. The first one was 2 miles or 3.25 kilometers, then 4 miles, 6.5 kilometers. Then we went to 14 miles, and then we went to 25 miles. So we had quite a few QSOs. And when you start, when you get things aligned and you run all the bugs out of your system, these were easy QSOs. Easy. Here's Fred's signal. We sort of developed this little protocol where Fred would send 5 dashes, then a carrier, and then 5 dashes. And when you watch this, pay attention to the QSB as the carrier is up. You'll see there's, like I said, 2 different kinds of QSB. One is this long term. The other one is sort of flickering. Like when you look at a star at night, you see it flickering. So I'll run this. I think it's only 30 seconds or so, and take a look. Take a listen. By the way, down here, I don't know if, let's see. This is minus 90, 80. These are 10 dB per division, okay? Oh. Well, I guess that was one of the ones where we just did the carrier test. But if you look at this, noise floor is down here around minus 100, so probably wasn't completely dark yet. But from a peak to a valley of minus 70 right here to minus 55, 15 dB, oh, even more. 15 to 20 dB of attenuation. This was across 25 miles. So things are changing. Are changing in the atmosphere as you make these tests. Let's see. Is this another one? Okay. 25 miles. So I'm going to pause really quick, but look at the QSB on in between these letters, in these characters, and then look at this. See this slow moving QSB? So there's a lot of interesting stuff happening here. 20. Okay, so here's Fred doing another. These are 5 dB per division. This is another test. This is the 24 LED array that Fred runs versus 6 of those arrays. He has a stack of 4 high rows of 6. So we wanted to see, hey, is this possible? With only 6 of those LEDs. So Fred was putting a piece of cardboard in front of all the LEDs except for a row of 6. All right, so yet another blunder on my part. That should say 24 LEDs versus 6 should be 6 down here, along with its associated 5 to 10 dB of QSB, and this is the 24. I don't know, what would you say? 5, 10, 15, something like that? I mean, again, there's QSB to deal with. There's the fact that we're not using a real good test instrument, so we don't know the linearity. But SDR console provides a fair comparison, but so you get a good feel for what's going on. So one final test that we did, and that was I made a recording. SDR console allows you to make a signal level strength recording and turn it into a CSV, which you can then plot in Excel. So, and I did a little smoothing on this to get rid of some of the QSB. But so here's the noise floor as reported by SDR console, not including all these, right? This is just the constant noise floor. I don't know what went on here, but so it's reporting like what, 105 minus 105. That's with the SDR turned off. Let me see. Is that true? Disconnect the SDR. I don't know how he's making this, what bandwidth he's using to come up with this noise floor, but let's not worry about that. Let's look at here. Here's a carrier for, I don't know, 10 seconds with the 24 LEDs. Okay, Fred covered up 6 of the LED, or 12 of the LEDs, and you can see, there was a drop there. Probably not what exactly we expected, but remember QSB. And then after that, he covered up all but one LED. And if you look at the transmitter being off here at minus, let's say 75, that 1.8 LED was still potent at 14 miles. Here we're back on again with all the LEDs. So you can see there's a slight difference in amplitude there. And then the transmitter being off, so this was essentially the noise floor of the receive system. And then back to 24 LEDs again. But you can see that one LED at 14 miles would provide a usable QSO if you really wanted if you could, had a SDR and whatnot ahead of it. And here's where I disconnected the optical from the SDR. This was, I think, the noise floor. Let's see, disconnected SDR from the optical. Now, this was the noise floor when you actually turn the power off to the optical receiver. So minus 95 up to a minus 55 with 24 LEDs across 14 miles. This system has a lot of headroom, a lot more to go. And this was interesting. So here's Fred's transmitter. He uses the little PWM modulator to come up with his tone, and so you're able to play 600 hertz or 16 hertz or 16 kilohertz, whatever it is. But I wanted to show you. Here's two transmitters. They're 18 inches apart, right? And just as a joke, I figured out something 4.9 million wavelengths apart. This is a path from Fox Hill in Connecticut, 25 miles away. And the purpose of this was, hey, Fred, record these two signals for me and tell me what, the QSB looks like, since they're only a couple of inches. They're only 18 inches apart. So here was the result of that. I think this is a video too. Let's see, 14.4. This is my big array, and here's Fred's 24 LED array. So now, we know that there's going to be a big difference between 140 LEDs and 24. But what's interesting is watch this one moving up and down and this one moving up and down. These radios, these transmitters were 18 inches apart. Let me play this. So you can see that these were not coincident. Something in the path between those two was changing. You would think that, well, I don't know what you would think. This was just a curiosity, sort of an experiment that we did. Anyhow, you can see that this peak and this peak don't coincide. This minimum and this minimum don't coincide. They're like they have a mind of their own. Okay, so what's the next questions? So some things we're thinking about is, when it's dark, are we at the limit of the APD detector, or is there even more sensitivity to be had if it was dark, literally darker? More cloud bounce experiments, and you go back and look at some of my other videos, you'll see that, because antennas and transmitters have made huge advancements. One thing I'd really like to try is non-line of sight paths with someone, pointing up at the sky, at some common volume with the transmitter and receiver, and seeing what happens from there. Knife edge refraction, trees, buildings. A lot of these are questions because I don't know the answers, or experiment, paths for experimentation. Reflective paths. We both live 10 miles apart, and we have a water tower that's common to us. With a laser or really narrow beam widths, yes, you'd probably be able to make a path. What about fog? Fred was doing an experiment where it was a very humid night with another gentleman, and he found out that pointing was much less critical during not foggy, but very humid. And you can see that too. I have a street light here not too far from my house. It's at the crest of a hill, And when I'm down the hill, I can't directly see the beam, but I can see on a foggy night or a humid night, I can see the light scattering. So there's some interesting stuff. Take advantage of, an optical beacon. That's an idea that, an omnidirectional optical beacon, that's a possibility. And I'd really like to push the digital mode, Q65, to just see how far it goes. And rainbows and rain scatter, is that a possibility? I don't know enough about that. Anyhow, that's it. Questions? If you have any questions, I suck at typing. I really suck at typing. You can send me a question if you like, but I also might just ask you if you want to do a Zoom meeting and literally talk about this stuff. It's so much easier. And again, I suck at typing. All right, everybody, 73 from W1 VLF.